Hey there, this is Arnav from Pebble and welcome back to the Introduction to Linear Algebra series. In the last video, we discussed basis in dimension, and in previous ones, we talked about vector spaces, subspaces, linear independence, and all of those very interesting concepts in linear algebra. But for this video, I want to shift back into matrices, and I want to talk about a property of matrices that I find to be very fascinating, and that is row space. So, what is row space? How do we define it? Well, let's say we have a matrix like 1, 2, 3, 4, 5, 6. So this is a m by n matrix, right? So what is m? What is n? Well, m is going to be 2 and then n is going to be 3 because remember in matrices row come first and then columns. So we got a 2 by 3 matrix here. And so what if we consider each row in this to be a row matrix? Okay, and then if it's a row matrix, then we can call this a tuple. Okay, so if it's a row matrix, well, hey, 1, 2, 5, 1, 3, 5 rather, 1, 3, 5. This looks very similar to the tuples we've encountered in previous videos. So this we could say it belongs to 3 tuples, and so if this belongs to R3, and then we also have 2, 4, 6, which belongs to R3, what are these? These are row matrices, right? And then these are 2 vectors. So, well, we have 2 vectors, and from a previous theorem that we learned in the linear independence section, well, the span of the rows of these 2 rows is going to be its own subspace. And so we're going to call this subspace the row space of a matrix A. So row space. And so to formally define row space, the row space, it's going to be the subspace that's spanned by all the rows of our matrix. Okay? And another term to know is row rank, which row rank is the dimension. It's going to be the dimension of our row space. Okay, that's very important to know. So to determine whatever our row rank is, we need to obviously identify what's our basis for the row space that we get for our matrix, and then, that's pretty simple to do because there's a technique that will follow. Okay, so let's understand our technique. So the non-zero rows of a row reduced matrix are going to form the basis for that row space of that matrix. So if we were to take this and we were to row reduce it, well then, hey, whatever non-zero rows that we get, those are going to form our basis. Those are going to be the basis of our row space. And then how many, obviously from there, what follows is that dimension, that's going to be how many non-zero rows. So if we have 2 non-zero rows, well then, hey, that's 2 non-zero rows. That's going to be our rank, that's going to be our dimension. So it's actually really quite simple. It's really quite simple. Okay, so let's take an example here. Let me write it out really quickly because it's a bit of a long one. Okay, so take a look at this matrix that I've written out, and it's already in row reduced form for you, and all I need you to just tell me is the row rank of our matrix. Okay, well, you can see easily that A has, or this matrix here has 3 non-zero rows, so that's going to mean that our row rank is 3. And then from there, we can say that, well, what are going to be our basis for our row space? Well, that's going to be each row here because it's in row reduced form, and when we know in row reduced form, we can't none of the rows are going to be linearly independent. So this would be, this would be, and this would be, these are our three rows here that are basically just, those are going to be our basis, these three vectors. Okay, and obviously since most vectors are not going to be in row-reduced form, you need to get them into row-reduced form. And this isn't going to change your row space because they are elementary row operations when you're doing this. Okay. And so one thing to note here is that if you have some matrix B that's obtained by A, let's say this matrix is A. If you have a matrix B that's the row reduced form of A, or it's any matrix that you obtain by using an elementary row operation on A, then the row space of these two are going to be the exact same. Okay? Basically, what this is saying is that no matter what elementary row operation you do to a matrix, the row space is not going to change as long as it's an elementary row operation. Okay, so one more example. This one's pretty simple. I'll write it out real quick. Okay, so we need to take a look at this example real quick, and I'm going to say this is A. So first step to determine the row rank and the row space of this, the basis for the row space, we need to transform the matrix into a row reduced form. So take a moment to do that. I'm not going to do it because this should be something you should know at this point, but take a moment to do that. Okay, so when you do that, you should get that your first row is going to be 1, 3, 4. Your second row is going to be 0, 0, 0, 1, 1. And then you're going to have 2 0 rows after that. And so from here, you can easily say what the row rank here is. It's going to be 2 because this is our transfer matrix. So we can say this is B, row reduced of A. And so the row rank is clearly 2 because we have 2 non-zero rows in row reduced form. And then the basis vectors are going to be these two, which are our row reduced rows. So 1 through 4 and 0, 1, 1. Those are going to be our row reduced form vectors, for which are their basis. Okay? And so one application of this is going to be more so for finding basis. So if you're given 3 vectors and you need to find the basis for the span of whatever those 3 vectors are. So I'll give you an example really quickly. So let's say we need to find the basis for the span of S here. So if we take the span of S, well, we need to find the basis for these 3, for whatever it is that these 3 vectors span. And so this is a bit of an annoying task to do, so we're going to use matrices here that are going to simplify our process. So what if we just use what we know here and we create a matrix with each of these vectors being our rows. So if we create a matrix like 2, 6 minus 2, 3, 1, 2, and then 8, 16 minus 3, well, these are each our vectors, each row. So the span of S is just going to be the row space of this matrix based on what we know. So if we row reduce this to obtain 1, 3 minus 1, 0, 1 minus 5 eighths, and then 0, 0, 0, well then we can get that the dimension of this is going to be 2. So the dimension of the space of the span is going to be 2. So dim. So dim s is going to be equal to 2. And then our bases, the two vectors in our basis, which are going to be the rows in the row reduced form, are going to be 1, 3, minus 1, and then also 0, 1, minus 5, 8. And so these two are going to be our basis. And obviously, you just need to transpose these just to turn them back into our standard vector notation, which you don't need to write out, but just know that that's how it works. Okay, so this technique is extremely useful in finding the basis for the span of any vectors. You could even do with polynomials. So if you have vectors that belong to the vector space P2 or P3, then you could just turn that into a matrix and then row reduce it, and then those are going to be your row space, and whenever you transpose that, they're going to be your basis for your actual span of your actual set. Okay, so that's pretty much the general idea of what we can use row space for. And one example that I do want to give you is with what if your vectors are, well, matrices, right? Because the matrix space is also a vector space. So what if your vectors are matrices? Well, how do you go about finding the basis for that? Let me write out a problem really quickly and then we'll try it. So here we have the set R, and the set R is 5 vectors that we need to find. Well, we need to find the span of these vectors, and from there we can get the basis. Okay? So we need to create representations that are column matrices, or rather coordinate representations, with respect to a standard basis. And with respect to a basis is something that we'll learn a bit later, but just note that we're just trying to convert this into a column matrix that we can transpose into a row matrix to fit in our matrix. Okay, so the general idea here is because we have they're all the same dimension, right? What we can do is, let's say this is a matrix like this is a matrix like this is a matrix like this, and then this is a matrix like this. Okay, so we can split them all into the different a number in each different spot in the matrix, and then we can create this matrix out of, oh, my apologies, this should be a 0. Okay, yeah, I think that's, let me double check. Okay, good. So what we can do is we can represent this matrix up here as a combination of these 4 matrices. So this one is just going to be one of the first matrix, one of the second matrix, and then 0, 0. And then the second one, second matrix, well, that's one of the second and then one of the fourth. So that's going to be 0, 1, 0, 1. And then so on and so forth for the other 5 matrices. So we'll get 1, 0, 0, minus 1. And 0, 0, 1, 0, 0, 1, minus 1. And then also the fifth one is going to be 0, 1, 1, 0. And you might be wondering, how did I get these 4 matrices to merge together to mix and get this? Well, these are a basis for 2 by 2. These can form any vector inside M2 by 2. So we're just taking, remember we learned what a standard basis is. We're taking just the standard basis and then we're just representing each of our vectors here in terms of our standard basis and then combining them into our row matrix. And so now that we have all column matrices, we just transpose each one, put them into our matrix, find the row reduced, and I'll leave that as an exercise for you, but once you do all that, then you should get your I'll give you a hint, 3 non-zero rows, which means your row rank is going to be 3. So 3 non-zero rows, and then those are going to be your basis for the space R, for the span of R. Okay? And then once you get the transpose of each of the non-zero rows, you need to then use this technique that we used here to convert them back into matrices because, well, we have matrices and not single vectors. Okay? And that gives us one more theorem. So if you have a set of some number of n tuples, and if you have a matrix that has all of the n tuples in its all of the n tuples as its rows. So if you have, let's say, 500 n tuples, well, then the idea here is that you would have A would be a 500 by n matrix, basically. So you have 500 rows, each row would be one of the n tuples in your set. And so if you have that, well, that's going to be linearly independent if and only if A is equal to 500 or however many elements are in your set. And that's pretty useful to quickly understand whether your rows are going to be linearly independent, and that's also going to help you to find inverses, and that's one of the other rules for finding inverses. Okay, and so you can also use that if you get a set of matrices, if you get a set of vectors rather, you can put them all into, I guess, a matrix, and then you try and solve that matrix. You try and solve that matrix as if you're finding the row reduced form, and if you have a row rank that's equal to however many you had in that original set, then you're going to get linear independence. And so that should conclude row space. And in the next video, we'll continue on with more of rank. But yeah, I'll see you then.